Good morning, everyone. A warm welcome to the Founders Day celebration at Indian Institute of Astrophysics. Each year on 10th of August, we gather to honor the legacy of our founding director, Professor Venu Bapu, on his birth anniversary. Today, we commemorate his remarkable contribution to Indian astrophysics with the prestigious Founders Day lecture. The origin of Indian Institute of Astrophysics traces back from the Madras University, which was established in 1786. I think the formally started operating in 1790s. It was one of the oldest observatories in the world. Over the time, this Madras Observatory evolved into the Kodaikanal Solar Observatory, and that became the center for the solar and stellar research. However, under the dynamic leadership of the Professor Bapu, when he moved from Nainital to Kodaikanal in 1960s, this institute underwent significant transformation. And then recognizing the need of modern, well-equipped Center for the Astronomical Research, the Professor Venu Bapu spearheaded the establishment of Indian Institute of Astrophysics in 1971, and later it moved to the headquarters moved to the Bangalore. And it was the formal establishment of Indian Institute of Astrophysics. He was the driving force behind establishing the Kavalur Observatory, which was named later was named after him, the Venu Bapu Observatory. And his vision and leadership laid the foundation of IIA's emergence as the leading institute in the field of astronomy and astrophysics. Bapu also made many scientific contributions. Among them is the well-known Bapu-Wilson effect. So today we are celebrating his birth anniversary as a Founders Day lecture. So over the years, many prestigious personalities from the field of science and technology has delivered their Founders Day lecture, enriching us with their insight and the knowledge. In the last 2 years, we had privilege to hosting Professor Sujatha Ramthorai from University of British Columbia, Vancouver, and then Professor T. Ramaswamy, former Secretary of Department of Science and Technology, Government of India. This year, we are equally delighted to welcome a distinguished speaker for the Founders Day lecture, Professor Umesh Waghmare, President of Indian Academy of Sciences and the Professor at Jawaharlal Nehru Center for Advanced Scientific Research. To begin today's program, we will honor Professor Bapu's memory by garlanding his bust. So I will invite Professor Waghmare and Director IIA Annapurni Subramaniam to garland the Bapu's bust and join us in this tribute. I request Professor Annapurni to welcome today's esteemed speaker by a bouquet of flowers. We take this opportunity to make another important announcement. So IIA has instituted an award based on the best instrumentation paper lecture, and this initiative was spearheaded by Professor Rangarajan, our former dean and faculty member at IIA. I think he is with us today. So I request Professor Annapurni Subramaniam to make the announcement for the awardee.
Good morning all. Welcome to the Founders Day program. And I welcome Professor Umesh Waghmare for this program as well. And in this year, we are introducing to announce the winner of this particular lecture, instrumentation lecture. From this year onwards, we'll have this announcement on Founders Day as per the wish of Professor Rangarajan. So this is the first announcement for the year of paper published in calendar year 2021. So let me read out the preamble for this award so you know what it is about. So the Institute has instituted a lecture for the best instrumentation paper every year since 2016. This is an initiative by Professor K. Rangarajan, former Dean and Faculty of IIA, who is deeply interested in the development of astronomical instrumentation at IIA. So IIA scientists and engineers at level of associate professor or engineer E and above are eligible to nominate a published scientific paper for the consideration of the lecture. The following criteria apply. The paper published in the reference journal during the calendar year 2021. So it's just basically a year before can be considered for the selection this year. The paper may contain calibration done with an instrument, the laboratory and instrument done with instrument and the laboratory and preferably field tests performed. The instrument could be a subsystem of a major instrument as well. The first author of the paper should be below 40 years of age as on 31st December of the calendar year 2021. The first author should be on the payroll of IIA, either as a student, PDF or faculty during the calendar year for that particular award. So the nominations were sought around February and we completed the formalities, and then now we are announcing the award. There is a committee constituted to select, go through the process and select. So I'm pleased to convey that the committee consisting of eminent scientist experts have carried out screening of the papers and the published journals during the year and selected the following paper as the best among the whatever papers that are screened in. So this is Girish et al. Consisting of all this Girish, Katharaman, and Indrajit Barve et al. So this basically the paper has titled Radio Interferometric Observations of the Sun using commercial dish TV antenna. This paper is published in Solar Physics. So our authors, I repeat, Girish, Katharaman, Indrajit Barve, and Ramesh. So this is published on 17th August 2021, accepted on 23rd July 2021 in Solar Physics. And this is selected, and we have congratulations to all the authors, and we have Girish here. Girish, he's an engineer, he's based in Coordinated Radio Activity. So we have a gold medal instituted by Professor Rangarajan, so that will be given. And the award is for the lecture. The lecture will take place in a couple of weeks from now. That time we'll be giving the certificate with the citation, etc. So right now we are announcing and the presentation of the gold medal, and we invite Girish, and congratulations to all the authors. I request Rangarajan also to come over, please. Yeah, and I request Professor Waghmare to give the gold medal. Do we have other authors of the paper here?
Probably online.
Yeah, we will have it during the lecture, and we'll have it.
Thank you, ma'am. Thank you.
Thank you.
Thank you. We have many IIA staff who have joined this event online. We have many field stations. Our field station staff have joined online, and our scope, which lead our effort in the public outreach, has organized the live streaming on the YouTube. So there must be a lot of audience in the YouTube as well. So we welcome all of the online participants. Now I would like to invite Professor Annapurni Subramanian to formally welcome the gathering and introduce our esteemed speaker.
welcome you all to the Founders Day lecture. And I'm very happy that Professor Umesh Waghmare has accepted our invitation and is here to deliver the Founders Day lecture. Thank you. Thank you so much for coming here. This is I just read out a short biodata of Umesh Waghmare. He's a very well-known scientist, but this is quite short, I believe. Professor Waghmare received the BTech with Institute Silver Medal in Engineering Physics from IIT Bombay in 1990 and a PhD in Applied Physics from Yale University in 1996. He worked as a postdoctoral research associate in Physics Department at Harvard University before joining Jawaharlal Nehru Center for Advanced Scientific Research in 2000, where he is presently professor in the Theoretical Sciences Unit and a J.C. Bose National Fellow. He is presently distinguished adjunct professor at Temple University and the president of the Indian Academy of Sciences. His research interests include ab initio modeling and simulations of multifunctional materials, mechanical behavior, 2D materials, quantum geometry, topological insulators, and materials for energy and environment. He is an associate editor of Nanoscale and Nanoscale Advances. There are several awards, some of them being he is a recipient of DuPont Young Faculty Grant Award 2003, MRSI Medal 2004, BM Birla Award for Physics 2005, DAE Outstanding Research Investigator Award 2009, IBM Faculty Award 2009, SS Bhatnagar Prize in Physical Sciences 2010, and Infosys Prize in Engineering and Computer Science in 2015. He was recognized as a distinguished alumnus by IIT Bombay in 2017. He is a fellow of the Indian Academy of Sciences, National Academy of Sciences, Allahabad, the Indian National Science Academy, and the International Academy of Engineering. So we are very, very happy to have you here at Professor Waghmare, and I welcome you to deliver the Founders Day lecture. Thank you.
Thank you very much, Professor Annapurni. It's a pleasure to be here in IIA. I have known many scientists here as colleagues, friends in various capacities, but it's my first visit and I'm really delighted to be here in this very special institute today on a day which is also very important to the institute and also the astronomy in India, particularly the Founders Day of IIA. MKV Venu Bapu, of course, is the founder of IIA. I don't need to tell you that, but I must say that IIA has a very long history. I read up, running into 200 years. It's a very rich history, and starting from Kodaikanal Solar Observatory in 1899 particularly, and it's shaped into a very unique institute in India, I feel. And to celebrate Dr. Bapu's birthday is, of course, to remember his accomplishments in astronomy, but also his contributions in setting up institutions like this. And let me appreciate that IIA has grown into a very fine research institute, making impactful contributions in various domains. With presence in different parts of India, which is also not so common for an institute of this size. And more importantly, connecting with society and other institutions locally as well as globally. And that's also not common. Most institutions don't have such a strong connection with the society. And I see that there are more than one ways I feel IIA connects with not only scientific fraternity, but also society at large. So it's really nice for me to be here on this day to appreciate the legacy of Dr. Bapu, continue through the activities of Indian Institute of Astrophysics, which is also reflected in the recognition of Professor Annapurni Subramaniam with the inaugural Vigyan Shri Award in Space Science and Technology. That also reflects how these contributions are going into other areas of science and technologies as well. So it's great to be here. Congratulations. It also reflects on the institution, I feel, to such a great recognition. Dr. Bapu was also a fellow of the Indian Academy of Sciences, which I represent here as the president. And Dr. Bapu was vice president of the academy during 1980 to 82. And the academy is very proud to have him as our fellow. And I am delighted that I can be here to celebrate his birthday with you today, representing the Indian Academy of Sciences. So I'll take a few minutes to tell you what Academy is thinking these days, in particular connecting with the scientific ecosystem in India. It's the 90th year of the Academy. It was founded by Sir C.V. Raman in 1934 with a mandate to promote progress and hold up the cause of science in the country. And Academy has been very active. So at present, we are looking very proactively on how we can strengthen the scientific ecosystem in India. I'll tell you the background is the number of researchers, funded researchers per million population in India is much lower than most countries who are in top 5 or 10 in science and technology, including, of course, United States. We are 6 times smaller in this number with respect to United States, and of course, even worse with places like South Korea. The second is we are subcritical in strength in most of the emerging areas in science and technology. This is also unfortunate, but it's true. Of course, this is not to disregard that lots of good works are coming out of India, but they don't add up in overall measure to sort of what we would expect of a country of our size. So enhancing the fraction of national GDP that is to be spent on science and technology, research and development is of course one obvious thing to do, because you can see we spend 0.7% of the GDP today on S&T, which compares with about 2% being spent by United States and close to 5% by South Korea. And just to give you historical comparison, South Korea got independence exactly on the same day as India, 15th of August 1947. And of course, they have the advantage of being small in size in managing and sort of planning the growth, but certainly they have relied very heavily on investment in research in S&T. And that's reflected in where they are today in sort of many domains of science and technology. Yeah, so definitely there is a room for us to increase the funding in terms of fraction of the GDP being spent on S&T. I hope I'm okay to talk about this because then I'll go into my technical talk eventually. I have been fortunate that Annapurni has given me enough time to talk about these things, so thanks. And but if this is boring, I can skip this and go to technical things as well. Okay, yeah, so indeed, how do we, suppose the budget is increased tomorrow to 1% of GDP. Do we have an action plan to make use of that funding in a way which is actually fair, inclusive, and respecting diversity and equity in science and technology? And the answer, unfortunately, is not so simple to that. Okay, so if we want to recommend to government to increase the science and technology budget, we also need to have some suggestions on where that fund can be directed. And there we are also at present focusing on universities. I must acknowledge that some of this was prompted by interaction with Dr. Karandikar, who is the secretary of DST, and also Professor Ajay Sood, who is the BSA presently. So universities are a huge resource. They have a large landmass and lots of room to grow. Yeah, unlike the campuses we often visit and work in. Secondly, it's a great option to scale up the number of researchers because of the first point. Yeah, I mean, lots of students join universities and they are our future. The young generation is our future. Of course, there is a huge potential to excel in science and technology as well as art and humanities, which is not the case in most of the premier institutions today, where the focus has been mostly on science and technology and often on undergraduate, or it is only on research. So there's a separation between undergraduate education and research, and there's a separation between art and humanities and science and technology. And both these gaps of separation can be addressed if we invest in universities. And that's, at least in my tenure at the academy, this is one thing we are trying very hard. So we had a brainstorming session and have basically come up with a detailed work plan or project proposal where our plan is to try to connect all stakeholders, which include institutions like this, universities, industry, and government funding bodies as well, much better than they are connected today. There is very little dialogue between institutions or different departments or wings of the government, and that should also improve. Develop collective thinking and cooperation, which I feel is also linked partly with the fact that we are subcritical in these numbers. So collective thinking is really important because we are subcritical, and that will mean we share ideas, share problems with each other, and come up with solutions in sort of joint activities and collaboration. So the philosophy is to grow together. And this is where I wish to highlight that we are not looking at universities as weak players in the ecosystem, but equal players which we need to grow together with by mentoring, sharing, and by achieving diversity, equity, and inclusivity in whatever we develop. So, of course, we have plans to set up regional hubs in various parts of India, of the Indian Academy of Sciences, which will engage with local state councils and agencies in science and technology. We also have to plan to set up something like Aspen Center for Physics in Bangalore, and later in other parts of India, where we will provide a space where a lot of people or a group of people can come together for interactions during their summer months or suitable period during the academic year, and develop good sort of promote collective thinking and a few other things like having young faculty members in universities. So this was not based on just hypothetical ideas, okay? So we did a very scientific and rigorous sort of analysis. We involved people from universities, particularly the junior faculty members from all over India, from Jammu Kashmir to Kanyakumari to Jharkhand, and took their view. Also, we conducted a survey with about 40 questions, identifying the gaps they face in the universities. And of course, if I have to just briefly tell you, the principal gaps are most universities have less than 50% of the faculty members on the roll. And that has, of course, cascading effects. They have to teach a lot more, less time for research. Administration is not so strong, so they also have to contribute to administrative work. So there is a clear problem in terms of that. So setting up mentorship program which will closely link with the junior faculty of universities. So that document will be available on our website of the academy very soon. And we took input from lots of people, okay, not just fellows, but much wider sort
But
of.
also the focus has to go much more on the quality rather than number.
Absolutely, yeah,
Should
yeah. No, so
stress should be on quality.
definitely.
But
So
otherwise it's a counterproductive.
yeah, no, so that's where the mentorship is. See, just giving faculty members in universities is not the proposal. Idea is to link some of the well-performing senior scientists, not just fellows but others as well. Link them with the junior faculty when you recruit them in universities. Let them work together and develop sort of yeah. I agree with you absolutely. Quality is very crucial. In fact, if you ask in terms of number of publications, we are outperforming most other countries today. But in terms of impact, we are really nowhere.
It's a counterproductive. Sometimes,
Yes.
oh, we are spending so much money, a lot of papers, there is nothing.
Yeah. No, that's absolutely not the spirit here. Yeah. So, see, that's where I said the collective thinking to develop good ideas. So, Yeah, it's a long discussion. We can certainly talk about it after my presentation. But definitely, like, I think having good ideas to work on and developing cooperation is crucial to achieving quality. Okay, so we are not just saying increase number, give them small little things. That's not the idea here. Yeah. Thank you. Okay, so that's where the academy is heading. One of the first sort of things we are thinking of doing is to develop academy science and technology cloud, which will be a digital sort of image of knowledge and human resources of India. And this will include basically problems, ideas, capabilities, expertise of people, funding opportunities, and job openings in various places. And this cloud will, of course, have mentees, which are junior faculty in universities, which will be linked through this hub to fellows and mentors. And industry will be closely linked with universities. And that sort of is the spirit in which this is being developed. And you will wonder why this is a need of the hour. Look, this is revolution driven by data science and analysis. And if we don't have reliable data, which actually is a very serious problem in India, we don't have reliable data, and if we, as a result, we can't really benefit from it. You know, there's a repetition of works or there's lack of cooperation. So this is really to have very easy access to information about, you want to solve some interesting problem, whether you're from industry or academia, who are the people you can interact with, or where are the resources you can make use of. You know, that should be very easily possible. And although some of this is available on websites of individual entities or institutions, to have a single cloud which will integrate it into one single body and then use AI tools, I must say that I know there's a lot of criticism on use of artificial intelligence and machine learning, but believe me, it is going to be there everywhere. And it's not like it will throw people out of jobs, but you really have to be smart to make use of those tools with very significant domain knowledge, niche knowledge areas. So we will certainly use AI ML in sort of identifying strengths, gaps, and then do the planning. So that's where academy is thinking, in addition to, of course, developing things on the ground. Okay, so thank you. After this about 15 minutes of general chat, I'm going to switch to some technical work. This is very different from what you often see in astronomy, or generally typically see in astronomy. The only sort of contact is many of the instruments you use do benefit and rely on the materials that we use or talk about or develop deep understanding about. And actually, I'm very proud to present this work here. This work is about sensing vibrations using quantum geometry of electrons. The reason I think it's appropriate for this kind of an event is it represents, it connects with two major scientific ideas to have come from India. One is Raman effect, which of course is one of the most impactful works to have come from India. And Raman effect, if some of you may not have known before, it essentially uses light to listen to vibrations of a system, whether it's a molecule or a crystal, right? So it uses light which gets scattered by the vibrations, and the change in the frequency of light gives you the frequency of vibration. That's very basic description of Raman. And it is very powerful because vibrations often are fingerprints of a system. Yeah. So, for example, now you have listened to me for 20 minutes. Even if I speak outside the hall among many people, you will guess that that is Umesh who is speaking. That my voice is my fingerprint. So Raman is in some sense like that. Okay, and that's why it's powerful. It's used in biology to nanoscience to all sorts of areas. The second important idea to have come from India, scientific idea, and particularly Bangalore, is the Pancharatnam phase. And I'll introduce that to you in a little bit. And the work which I will present combines sort of the theme of Raman and Pancharatnam, but the mechanism is very different from what Raman does. So it's a really new type of spectroscopies that we are proposing, essentially based on theoretical analysis. So I'll sort of, that the idea of this lecture today is to give you a very simple introduction to what theory can do and what that theory is, and what we have accomplished using this theory. Yeah, that's the plan. And since this topic is very different from your day-to-day work, I would be happy to take your questions. In fact, any question will help other people in the audience possibly, so please don't hesitate to stop me and ask. Yeah, although I have kept the level very simple, not going into details, just to give you the flavor of what is happening. Okay, so our proposal for this new class of spectroscopies is based on first principles theory, and it basically coming up with a new class of spectroscopies which rely on quantum geometry. And many of these terms may not be familiar to you, right? What is quantum geometry? I guess spectroscopy is known to all of you, and of course some of you may not know first principles theory either. So and so we will demonstrate it with a vibrational spectroscopy of 2D materials. So of course, what is first principles theory? And that's my first job. So in astrophysicists probably are familiar with standard model, and which is used in particle physics or in many different things, and very successful. So similar model I will introduce to you, which is used in study of materials in a very simple manner. Okay, so it's the standard model of materials, basically. And based on that, then we will show the work that we have carried out. So, fundamental ingredients of first principles theory or simulations is essentially how atoms interact with each other via electrons. It's not very different from someone saying how quarks interact with each other using gluons, right? So, it's called first principles because we do not take any input from experiment in carrying out such analysis. That's why some people call it ab initio in chemistry. We call them first principles. So goal is how do these atoms interact with each other, and most applications in day-to-day life on the earth, the energy scales that we span are governed by how this happens. This is an example of catalysis, how carbon dioxide can be converted into something useful, or carbon monoxide. Whereas if you're thinking about a material used in jet engine, because of which we can fly, by the way, from one continent to another today, that also involves the same type of interactions. How atoms interact with each other and come together to form a material and give rise to the properties that you can make use of in technologies. So the first principles theoretical description of a material is basically a collection of nuclei and electrons that interact via electromagnetic fields. Then nuclei, here shown as spheres, are much heavier than electrons, and electrons are shown as the wavy particles. They are much more fast, and whose d log wavelength is comparable to the interatomic spacing. So nuclear motion is treated using Newton's laws, whereas electronic motion is treated using wave mechanics or quantum mechanics. So for any snapshot of positions of nuclei, right, we call it configuration in statistical mechanics, electrons are so rapid that they instantaneously redistribute themselves or distribute themselves to minimize the quantum mechanical energy. In quantum language, they fall into their many electron quantum ground state. Yeah? So given a structure or positions of atoms, electrons in very efficient manner fall into quantum mechanical ground state. This is called as the adiabatic or Born-Oppenheimer approximation. And that's one very important approximation that enters into this analysis. But you know, it's very rarely violated, at least in the day-to-day applications. One place where it is violated is the RDX, which is used in exploding bombs, where usually the very rapid release of energy comes from the fact that electrons get excited and move at the time scales which are comparable to motion of atoms in the chemical. So after you do this, you basically, for a given configuration of atoms and electrons, you have total energy which describes the sort of minimized energy of that configuration, minimized with respect to the electrons within the framework of quantum physics. So just a little bit more precisely, what is this total energy function? It is a function of atomic numbers of atoms which make that material, and also the positions of atoms which make that material. In chemist language, the first one tells you the chemistry of the system. If you have silicon, you have 14, you have carbon, you have 6. So an Ri basically gives the structure of a material or a crystal, right? The positions of atoms define the structure, whether what is the crystal lattice, or is it amorphous, or molecular structure is defined by the second one. So the total energy is a sum of two terms. One is the simple one, electrostatic Coulomb interaction between positively charged nuclei, and the second one is the quantum mechanical ground state energy of electrons for the set of Z ions. Unfortunately, this is not a simple problem because it's an interacting many electron quantum problem, and you can't solve it exactly for any realistic system. So there are techniques like quantum Monte Carlo which are available today where you can solve that problem more or less exactly, but those calculations are way too expensive with the computing resources we have. So what we do in the work that I'll present is we use density functional theory, which was developed by Walter Kohn and his colleagues, which showed that this ground state energy of electrons is a unique functional of charge density, electron density, and it's variational with respect to charge density. So the reason why it becomes very powerful is you no longer have to work with the many particle ground state wave function, which is a function of 3n variables. Now you have density, which is just function of x, y, and z. Yeah? So that's a remarkable, and that's an exact theory. What Walter Kohn showed is, if you know the ground state density of a many electron system, you know the ground state energy in a unique manner, or the potential which gives you that ground state in a unique manner. Of course, this is not enough to do practical calculation because they showed the existence of the functional, but not the specific functional which will do that job for you. So the form of this functional is very complicated and not known. So we end up using next level of approximations to use some simpler form of this functional, learning from lot of knowledge that has been generated so far using quantum mechanical analysis. And that functional then you can feed in. Basically this total energy becomes interatomic potential, the interaction between atoms, and you can also think of it as a Hamiltonian or potential in a Hamiltonian of a collection of atoms. And then if you use this in statistical mechanics, possibly using molecular dynamics or Monte Carlo, which are typically the techniques to do stat make of many particle systems, you can derive thermodynamics out of it. Yeah? And of course, Walter Kohn received a Nobel Prize for Chemistry in 1998 for this work. So this is the first principles theory, very simple introduction, but it's very powerful. When I sort of started my PhD, this was in early 90s, to do some simple calculation, I would probably need a supercomputer on the central facility in the US. I can do that calculation today on this laptop in less than half an hour. Yeah, so the computing speed has increased by factors of 1,000 from early 90s, and the memory size has gone up by some similar factors. So that's why this kind of theory and simulations have become a technique in material studies, which is combining the advantages of experimental work and theoretical work. You can do both using this theory. In fact, there are many occasions when these theories have been used to correct experiment. You know, the interpretation of experiments was wrong, and the theory could go back and say, look, you revisit your experiment and see. So this is what is called as standard model by Marvin Cohen. He's one of the fathers in this field. And total energy is the interatomic interactions. You will wonder, what do we obtain from this total energy? How do we make use of it? I'll just give you idea about 3 levels of structure of matter that we can derive using this kind of a function. One is geometric structure, one is electronic structure, and one is dynamical structure. Okay, and properties of a material like elastic stiffness modulus or dielectric constant or conductivity, they are all linked to the derivatives of this total energy function. Okay, so in a very fundamental way, the total energy function captures the dependence of properties of a material on the 3 levels of structure that material has. So what are these 3 structures? Geometric structure, all of you probably can guess what it is. Yeah.
Sorry to interrupt, but just since you just given a very qualitative overview.
Mm-hmm.
For example, I can relate to the kind of thing that we do for neutron stars. There also there's many body theory that we're dealing with.
Yes.
Protons, soup, and things like that.
Mm-hmm.
Now, here at an operative, an operative scale, you are trying to do, obviously using density functions, right?
Mm-hmm.
Mean density, which is also done there. But are you using some field theory perspectives, for example, wave functions and things like that when you do the calculation?
Okay. Yeah, well,
The density can be expressed.
Sure. Yes. So, good question, Arun. And the theory that you referred, like Thomas Fermi theory, for example, is a nice example, which was thought of as in 1930s, whereas density function theory came up in 1960s, and it did have a reflection of Thomas Fermi theory in some sense. I didn't go into the historical aspects of it, but so the practical use of that function does involve writing density in terms of single particle wave functions, not many body wave function. So, but that's only a sort of convenience to separate out certain aspects of the function into kinetic energy and the rest. Yeah. So there is
Here I assume you're still doing it with Newtonian mechanics as far as the energy and
which energy?
Obviously the nuclei. And you said
Nuclear energy is
in vibrations and
it has 2 parts, I said, right? Yeah, it has 2 parts. Nuclear motion is governed by this as the total potential, that's the interatomic potential. So it has electronic ground state quantum mechanical energy there. Yeah? But the motion is classical, yes.
okay. So that is quantum mechanically doing.
Electrons, yes, that's right. That's right.
Only difference is that you are using density functions there instead of.
Absolutely, yeah. And it works for the range of densities that we often encounter in crystals and solids. Okay, so geometric structure is where atoms are located, and that basically is obtained by minimizing the total energy. If you minimize the energy, you get the structure. Minimize it with respect to atomic positions, and these are the typical pictures that we can derive then at the end of that minimization, and it of course has the right symmetry and so on. Experimentally, to derive this structure, you would use X-ray diffraction for a crystal, whereas we basically do minimization and can predict structure before experimental work as well. The second is electronic structure. Here maybe I need to give a little background that quantum number of a electron in a periodic system, like a crystal, is a wave vector, K vector, which is essentially 2 pi by lambda, which is called crystal momentum, and that's what is here on the x-axis in different crystallographic directions, and y-axis is the energy of electronic states, single particle electronic states, and these are occupied states, these are called valence band, and these are unoccupied states called conduction band. I'm sure you have seen it in BSc days in semiconductor physics, and the band gap basically defines insulator versus semiconductor. If the band gap is 0 and there is overlap between the 2 bands, you basically have these as the highways for free electronic motion, and that's why this is metallic. It gives you high electrical conductivity. So experimentally to get this, you will use electron spectroscopy, photoemission spectroscopies, whereas theory, this is a side product of a DFT calculation, first principles calculation typically. And the last one is phonons, the dynamical structure of a crystal. And here also what we show is the vibrational frequency as a function of wave vector. That's a quantum number of phonon state. In a periodic structure, you will see this is acoustic phonons and these are optical phonons, and the slope of these phonons tell you the stiffness of a solid, like elastic modulus, and how basically fast the sound propagates. Raman and IIA spectroscopies measure only the phonon frequencies which are given here. Near gamma point, gamma basically means zone center point, 0, 0, 0 wave vector in case this. And thermodynamic stability, of course, is governed by the vibration, thermal vibrations and fluctuations of a crystal as well. And experimentally, if you want to derive this full dispersion, you would need inelastic neutron scattering and hence access to a nuclear reactor. Whereas this figure has been obtained on a laptop like this in about 1 hour with no experimental input other than just atomic number and atomic positions. Okay, so this is my very quick introduction to what first principles theory do for you, and there are many computer programs which are available for free these days, and these are some of those websites from which one can just download these softwares and do calculations. And many problems can be tackled with fairly moderate computing resources. So all you need is good creative ideas and try them out. So it's a very powerful theory. So now I will come to the main theme topic of my talk. Using the theory that I just introduced to you, we will be sort of proposing a new class of spectroscopies which depend on quantum geometry. Now the next part of introduction is quantum geometry, because many of you may not be familiar with that. And that's actually, the spectroscopies also sort of celebrate the 100th year of Raman effect, and you will see the spectroscopies do everything that Raman can do, but much more than that. Okay, so this is one slide I'm sure I don't need to explain to the audience here, how the curvature of space-time affects the trajectory of light in the space-time, and the curvature is affected by gravitational bodies. Yeah. So similar thing can happen for electrons as well. Yeah. And in a crystal, if you apply electric field along x direction, you will expect normally electron to move along x direction, right? But not in a crystal typically. I'm not worried about scattering of an electron by lattice or impurities or anything at all. Assume you have absolutely perfect crystal. Yeah? But in fact, electronic trajectory can bend in a crystal, and that bending comes from the fact that the quantum structure of electrons is also curved. It has a curvature. And that's what I'll introduce to you now, what that curvature is. And that has very spectacular consequences on measurable properties, okay? So that's one similarity I can point out at this stage itself, that electronic trajectory also bends in a crystal if the quantum structure of electrons has non-trivial curvature or geometry. So let me start with something very trivial, very easy to follow. And this is, by the way, to introduce to you what is quantum geometry, okay? So let me start with simple idea, electric dipole moment. If you have a positive charge and a negative charge, the dipole moment is easily estimated by knowing charges and the distance. But if you have an infinite crystal, yeah, infinite crystal arranged with the same charges, and I ask you a question, can you estimate dipole moment for me of this infinite single dimensional crystal? If I use this as the unit cell, I'll get a dipole moment P. If I use another unit cell, periodic unit cell of the crystal, which is given by this box, I get minus P. And if I use yet another unit cell which passes through the atoms, I get zero dipole moment because of the symmetry. Okay? So this is to tell you that such a simple quantity as electric dipole moment is not well defined if you're talking about it in a single crystal. And in a real crystal, it's much more complicated because charges are not point charges like this. We just talked about charge density, so charge is a continuous distribution, so you don't know where to pick your unit cell, you will get different answers. You can have a continuum of answers for estimate of that. Such a simple quantity. And just to remind you, it's basically dipole moment is an average value of position operator. And position operator is not well defined in an infinite periodic Hamiltonian system. So, what about measurement? You will say, come on, we all use crystal dielectrics, we all measure polarization. But actually, what you measure is not polarization or dipole moment. What you measure is always a difference in polarization, change in polarization. Yeah? So you have a capacitor with a dielectric like this, you apply electric field and measure the displacement current, and that current, if you integrate out, you will get change in the polarization measure. Okay? So all bulk properties which you think we are measuring polarization always involve changes in polarization. So what I say on the last slide in terms of theory is not inconsistent with experiment. Yeah, absolute value of polarization is ill-defined. Okay, so redistribution of electrons within a crystal in response to time varying field lambda leads to flow of electric current through the crystal, and that if you integrate out, you will get a change in polarization. And it's not surprising that this polarization can also be path dependent. In fact, that was my first PhD project in '92, where we showed that this is non-trivial. In fact, it's not only non-unique, it's quantized. It's integer times quantum polarization. Let's not worry about that detail right now, but I'll move on. So the quantum theory of polarization, delta P, essentially involves relying on this idea that I developed in the last slide, and then it was shown by Kingsmith and Vanderbilt that you can do that integral exactly for a single crystal and show that it's actually polarization is related to this quantity. And now some of you will find it familiar expression. This is basically Berry phase type expression. K is the crystal momentum of electron, and you go from one end of the Brillouin zone to another end of the unit cell in the reciprocal space. This is typically known as the Berry connection. Okay, and this is the geometric phase. It has connection with Pancharatnam phase that I told you. If students here don't know what is Pancharatnam phase, I'll just quickly tell you what it is. So imagine this is a pen in my hand, and it's a vector in three-dimensional space. I hold this pen perpendicular to my arm, and then I move my arm without changing that angle. I take it to 12 o'clock position, 9 o'clock position, and bring it back to the original position. You can see that pen has rotated by 90 degrees. Yeah? And this angle depends only on the solid angle that I subtended through this closed path. And that's why it's called geometric path. It doesn't depend on whether I went up and came down, I did something else on the way. It's not dependent on that. Yeah? And Pancharatnam had done this in the context of optics. This was overlooked in quantum mechanics until 1984, when Michael Berry pointed out that this can also be having consequences in quantum mechanics, because in quantum mechanics, state is a vector in Hilbert space, and evolution of a state in a closed loop will pick up Berry phase or geometric phase. Yeah.
Why I can see that there is a parallel transport picture emerging.
Yes.
Could you elaborate on what is the space on which the transport is happening?
Yeah, the space is defined by the momentum K of a block, the electron in a periodic structure. So the quantum number of electron in a periodic system or a particle in a periodic system is wave vector K, which is defined within minus pi by a to pi by a, which is in 3D it becomes a unit cell of Brillouin zone, it is called, and the parallel transport basically occurs in that space of K vectors. Thank you. And since it's periodic, if you go from one unit cell to another, it's a closed path. essentially. That's where the closed paths come. Okay, so this was rather quick introduction. Sorry, but there are many technical issues which I have lost over, but the concept is very beautiful. Position operator in quantum mechanical science is not well defined in a periodic structure. And the way to deal with it is using geometric phases, and that's the expression. And it's not just theory. You will see the original paper is cited maybe 20,000 times now because it's the most practically used technique now to calculate polarization of crystals. Yeah? You end up using a discretized formula, discretized parallel transport, you may call, and it's very sort of powerful and simple to implement. You need 1 day's coding to do this calculation. Okay, so let me remind you what we learned conceptually so far. The polarization of a bulk infinite crystal is not such a simple thing. It involves measurement of flow of electric current, and quantum theory as a result gives you equivalence between polarization and geometric phase. And that's the geometric phase defined. And remember, gamma alpha, the geometric phase, is related to the average of position operator. That's something to remember from this. Okay? All right. What happens if you have two-dimensional crystal? You have wave vector which can be along x direction as well as y direction. You can have geometric phase which is picked up if you go along x direction and y direction, which is basically position operator along x and y directions. And correspondingly, you can write down the expression for Berry phases, and the Berry phase gives you average value of x and y. Now, this is the key result which will connect with the gravitational lensing I told you about. So, if I apply electric field along x direction, the momentum will change along x direction by electrostatic force acting on electron. And if electron goes from one place to another along this line, but while that happens, if gamma y changes, gamma y is the geometric phase along y direction. So electron moves along x direction, and we are looking at evolution of gamma y. If that changes, it means you have a drift in position along y direction as electron moves to the x. And that change will occur if the derivative of gamma y with respect to kx is non-zero, which is basically the Berry curvature omega z, which is the curl of Berry connection. So if Berry curvature, which is the geometric curvature of quantum system, is non-zero, you will see transverse velocity picked up by electron, just like light will bend at a gravitational body in analogy. Yeah? So that's the origin of this bending of electronic trajectory, and that's the reason we call it origin is in the quantum geometry of a system. So if you have a two-dimensional metal usually is characterized by a Fermi surface, where you have Fermi surface with occupied states in this region and unoccupied states in this region. If you calculate the Berry phase along this closed path, geometric phase, you get phi, and what one can show then is anomalous Hall conductivity is given by this simple formula, E squared by 2 pi h bar times phi. Now, the transverse motion of electron should remind you of Hall effect, right? You apply electric field along x direction and voltage develops along y direction. That's the Hall effect. But here it's called anomalous because you didn't need to apply any magnetic field to get this effect. Yeah? And that's the key. The magnetic field emerges from the quantum geometry, non-trivial geometry, as characterized by non-zero Berry curvature of electronic states. Okay, so this is a slight digression, but just to tell you that recently there has been a huge sort of activity in something called topological phases of electrons in crystals and topological insulator, for example. So if you do this Berry curvature integral in an insulator over the whole space of electronic states, you basically show that it's equal to Chern number defined here, and which means that even insulator has a Hall conductivity which is quantized, and these are called as Chern type topological insulators. Yeah. So this is a slight digression, but just to tell you for completeness that very important area in physics today, condensed matter physics, called topological insulators, also have origin in the same ideas as quantum geometry. Okay, consequences of symmetry, and I'll probably skip this because of lack of time, so I'll go forward and move on. So to summarize what we learned so far, we started with dipole moment. Dipole moment, all of you know, generates surface charges, right? P dot surface normal vector. And those surface charges in the context of topological insulators correspond to edge states. And that's the beauty of topological insulator. How is topological insulator different from a normal insulator? If I look at the surface of a topological insulator, it's purely two-dimensional metallic, meaning I cannot go from bulk insulator to vacuum without having a metallic surface. And the reason for it is basically you end up having edge states which are consequences of non-trivial topological geometry of a system. Okay, so just to give you analogy now, quantum geometry and the electromagnetism that you are familiar with, this is called geometric band theory, quantum geometric band theory. The Berry phase is linked with basically Aharonov-Bohm phase in quantum mechanics. Berry connection is like a vector potential. Berry curvature is like the magnetic field strength, which is why you get this curved space-time here for electronic motion. And Chern number is like a Dirac monopole. The last point, although you may not follow it in detail right now, it's important. What it means is, if I have electronic bands which cross each other like this, linear crossing, that point, which is often known as Dirac point or Weil point, that point acts like a monopole to give rise to magnetic field around it. Yeah? And that's how the electrons, so in gravity you have a heavy star which deforms the space-time. Here is the Dirac point which modifies the geometric curvature and bends the electronic trajectory. That's sort of is the analogy.
Umesh,
Yeah.
one question, this Chern number, that's an integer.
Yes.
Is it, but when you do the flux, actually it's what we call analogous to a flux. But there it's not clear that it should be an integer. I mean, it could be.
Yeah, that's what I said. For a metal, if you integrate it in a for metal, it's not an integer. It's a continuous. That's why it's called anomalous Hall conductivity.
Okay.
But if you have insulator where you have basically full integration, it has to be integer. And yeah. Okay. All right. So of course, symmetry is quite restrictive, because if you have time reversal symmetry, Berry curvature is an odd function of k, and if you have inversion symmetry, Berry curvature is an even function of k. Unfortunately, it means most systems like silicon, aluminium, copper, they will have vanishing Berry curvature everywhere in k space. No, not any value, right? So indeed, this is not common as of now. There are very specific systems where these kind of effects are seen. But hold on, we will show you that you can use it still in many different types of systems. Okay, so there is something called as nonlinear Hall effect. Because symmetry is very restrictive, one went to study nonlinear effects, meaning if I apply electric field to a crystal, I break inversion symmetry. Right? So you use applied field to break inversion symmetry, and if you do that, there is an asymmetry in the sort of electron occupation or electron distribution in k space, and that allows you to have basically non-trivial Berry dipole moment. It's called Berry curvature dipole, which is the first moment of Berry curvature in k space. Yeah. So if you apply electric field, you lower inversion symmetry and you can have non-trivial Berry curvature dipole. If that is the case, you can show that Hall effect actually is quadratic in electric field, and the proportionality constant is given by this Berry curvature dipole. Yeah. So Berry curvature dipole is also a property of quantum geometry of electrons, a specific moment of the curvature metric. And if that is non-zero, you will see nonlinear Hall effect. Means you apply AC voltage with a frequency omega, you will have a Hall voltage with a frequency 2 omega or 0, like rectification, like second harmonic generation you may be familiar with. Okay? But again, with no magnetic field, so it's called anomalous nonlinear Hall effect. Okay, and that's very powerful because you see the anomalous Hall effect is linear, but then what happens is at the same frequency you have an electric current which goes along at an angle to the applied field. But in this case, nonlinear Hall effect, the Hall signal is at double the frequency, and applied field is only at a frequency omega. So your applied field always is Hall signal is always sort of easy to measure. It's always perpendicular to the applied field. Yeah. So that's the advantage of nonlinear Hall effect, and it was demonstrated experimentally in 2019 in a compound called tungsten telluride. Don't worry about the details, but basically it's a Weil semi-metal, and I told you Weil point is like a monopole of a Dirac monopole. Yeah. So nonlinear Hall effect simplifies things. It relieves the symmetry constraint in at least partial way, and it is visible. Basically, what happens is in tungsten telluride, you will have Berry curvature whose distribution is shown here in reciprocal space, and it has a non-zero dipole moment. If a system has a non-zero Berry curvature dipole, it will exhibit this nonlinear Hall effect, and that is well established now. Okay, so our work basically shows that you don't have to have a very special crystal like tungsten telluride to break symmetry and then have this type of effects, but you can also dynamically lower the symmetry. That's the key fundamental thing we exploited, right? Let me explain what we mean. When you have a vibration in a crystal, it can lower the crystal symmetry or a molecule, right? Not all vibrations preserve the symmetry of the structure, right? So if you have a vibration which breaks symmetry, lowers the symmetry, you can have basically similar effects visible. So the idea is you have dynamical excitations like vibrations, which will modulate Berry curvature dipole with the same frequency or period of time as the vibrational excitation. And then what we do here, I'm going to skip some of the mathematics, but we show that you have a Hall current which is developed due to this quantum geometric effects. The first part depends on the Berry curvature dipole, and that doesn't have to be present in all materials. But what we show is this part, which is derivative of Berry curvature dipole with respect to vibrational amplitude. If that is non-zero, you can have Hall signal at all of these frequencies. Yeah. So modulating Berry curvature dipole by a vibration oscillation creates oscillations in quantum geometry. Like in black hole, gravitational lensing case, if for some reason the heavy gravitational object was oscillating, you should see oscillations in the signal that you see, which is modulated by that oscillation frequency. So that's exactly what we are doing here. But here it's much more realistic because that oscillation is in our hand. That's the applied voltage that we apply in a device. Okay, so the present work basically we did lots of careful calculations to establish all these things. So let me give you now the basic idea. This is tungsten telluride monolayer shown here in the structure, and these are the vibrational excitations of that system. I am pointing out one particular phonon here, longitudinal acoustic phonon, which is basically the strain oscillation. If this compound, this layer membrane oscillates in plane as shown by these two arrows, it has a frequency which is given by this particular vibration. If I distort the lattice by that vibration, you will see the electronic structure. Yellow curve is basically the undistorted lattice, but if you distort it by this dynamical oscillation, you change the electronic structure back and forth. And when you change that electronic structure, you also generate oscillations in the Berry curvature dipole, and that also has been shown from our calculations rigorously. And as a result, we will expect peaks at this particular sort of frequencies. Yeah. So let me move on. So this is sort of is the first spectrum that we predict. Sorry. Yeah. So let me tell you what the concept is, the device. Yeah. So this is the quantum material we have, yellow color. You apply electric field along x direction, and what we are going to measure is the signal along y direction. That's the Hall signal, and no magnetic field is applied. And what we predict is the vibrations of the compound can be, the frequencies can be measured if you measure the frequency dependent Hall current. That's the first, that's called, we call transport spectroscopy. In Raman you use light. Here, in the first case, we use circuit. Yeah? So in circuit, basically Hall voltage is what is measured, and you will see, yeah, if you change the applied frequency, the AC frequency, this is the peak structure which develops. So the advantage of this spectroscopy is by changing the AC frequency applied across this channel, you can change the peak structure. Yeah. So. Yeah. Okay. So see, this is the nonlinear Hall effect to begin with. But now we change the AC frequency, and for changes in the AC frequency, you see the two peaks split out. And the splitting gives you this basically gives you the vibrational frequency. Yeah. So you not only will have one single measurement, but you can have a set of measurements to pin down a specific vibrational frequency. That sort of is the idea. The next is example given here, tungsten telluride, and again here you will see if I change the AC frequency, I basically alter the peak structure. And this is opening up a new technological possibility that if I have AC signal at gigahertz frequencies, right, I can translate the frequency modulation signal in gigahertz to terahertz, because phonon is the carrier now, unlike Raman. In Raman, light frequency is the carrier for Stokes and anti-Stokes. Here, phonon is the central peak, and these two are the peaks associated with applied frequency. So you have a new sort of technology which can modulate, sort of transduce signals from gigahertz to terahertz. Again, this is yet to be seen experimentally, so we are hoping some experimental work will happen in the coming years. So you will say that, well, the idea of dynamical lowering of symmetry works. You do have a way of measuring vibrational modes using this spectroscopy. Unfortunately, this is still very restrictive because you need non-trivial quantum geometry, and for that you need narrow bandgap crystals. You also need relatively low symmetry crystals. So what is the use? I told you that silicon, most of the compounds don't satisfy this condition. Yeah? So that's what we led to think of, learn from surface enhanced Raman scattering. If you are not familiar with it, in surface enhanced Raman scattering, if a given molecule doesn't have a Raman signal which is strong, you place it on top of a metal, and that electrostatic interaction between metal and the molecule enhances the Raman scattering from the molecule. Yeah? That's the idea of surface enhanced Raman scattering. So we use that concept in now proposing what is called as substrate-driven GQ spectroscopy, where we take an inert material like boron nitride. This is boron nitride, which is a very large bandgap two-dimensional material. We are working with 2D materials for convenience here, okay? Not that the technique is limited. The whole thing can be done for 3D as well. And the E phonon mode, E mode of HBN is given here. The arrows basically tell you how the atoms vibrate in that vibrational normal mode. And on the right hand side, we show the Berry curvature dipole that is induced by this vibration. Yeah? And indeed, it is non-zero. So what the actual apparatus that we propose to measure this is, you have graphene, which is the yellow background here, boron nitride, which is what you want to study using this GQ spectroscopy, which is deposited on top of graphene, and you shine light with a frequency omega L. In this case, we are using 2.52 terahertz because that's the laser available commercially from Edinburgh. And at that frequency, we predict what should happen. And what we expect is measurement should be taking basically the intensity of light, which is scattered with an electric field perpendicular polarization. And this is our prediction, that the central peak gives you the vibrational frequency like infrared spectroscopy, and the other two peaks basically give you the Stokes and anti-Stokes like scattered basically signal from this. Okay, so this is substrate-driven optical GQ spectroscopy, and you will see that this is the vibrational mode whose frequency we are measuring. You can see the animation, and if we change the light frequency, this is what happens to the peak structure. So by varying the probe light, you can easily sort of measure the vibrational frequencies, which is not so common and easy in infrared or Raman scattering. Okay, so it has some advantages, and in this case, it also opens up applications of quantum materials like graphene. Graphene has non-trivial quantum geometry, but it doesn't have the low symmetry to support this type of spectroscopy. So what we do is we use graphene and as a substrate or template material, which is quantum active, and use major vibrations of the another material which is deposited on
These
top
are
of it.
much weaker vibrations than the Raman one that we could identify.
No. So many of them are going to be Raman active. Yeah, some of them are IR active. Yeah. So we are not saying that. See, this is also a non-linear effect. So Raman effect, as you remember, was predicted by Dirac and Heisenberg in 1921, and it took overnight experiment by Raman to actually see it.
Yeah, but not having the technology to.
Yeah, because at that time there were no lasers, there was no high intensity field available. So for the first 20 years, it was purely academic interest. But once the lasers were available, it became much easier to do Raman spectroscopy, and now it's omnipresent. So I don't think this is going to be stronger than Raman, okay? We are not claiming that. But it is going to be complementary. It gives you information which is not always easily available from Raman or the line spectroscopy or infrared spectroscopy. And although we have shown it for vibrations, it can also be used for magnons or other types of dynamical excitations of a crystal. Okay, so this is how the real material GQ spectrum will look like. If you shine light on this tungsten telluride and measure the scattered light with a perpendicular electric field polarization, these are the peaks which will be developed, and you will see that there is similarity with IR peak, meaning these peaks are occurring at exactly the frequency of vibration, whereas these other peaks are related to Stokes and anti-Stokes type peak, which are separated by 2 times the light frequency of light. So it's a rich spectrum that we expect. Quantum picture of GQS is also possible, but we haven't worked out mathematical theory of it. In transport mode, when the AC frequency 2 times that is less than the vibrational frequency, basically excitation involved from the ground state to the first excited state like this, or from first excited state to this, depending on whether it's Stokes or anti-Stokes. And this one is more or less like Raman spectroscopy, where you go to a virtual state using applied frequency and then go back to the vibrationally excited state. Yeah. Now, please note that in Raman, this would have been just omega AC, the frequency of light. In our spectroscopy, it's 2 times omega AC, it's a second harmonic, and that's why it will be much more sort of contrasting with the incident light. This is another rectification related quantum picture. So let me close now very soon. The spectroscopy in fundamental sense is linked with Raman. Let me explain the fundamental similarity. In Raman spectroscopy, you basically focus on the dielectric constant, or for a molecule, its polarizability. So the question which is asked, the selection rule for Raman is, which vibrational mode changes the refractive index of a crystal or polarizability of a molecule? And that comes in the real part of this general dielectric constant. Whereas in our work, we have focused on sigma of omega, which is the optical conductivity or AC conductivity. And more than that, this hasn't been successful so far. Of course, conductivity has been known to us for a long time, but it hasn't been interesting because that coupling isn't strong enough. But if it is geometric, quantum geometric origin type of effect, we do expect it to have very robust type of measurable consequences. So that's why, in a way, it is linked with Raman. In Raman, basically you use a light frequency omega L and measure the frequency of scattered light. You have Rayleigh scattering at the frequency of light and anti-Stokes and Stokes line, which correspond to emission and absorption of a phonon. In our picture, basically you have light, two photons coming in or two AC fields coming in. They non-linearly couple with each other to give you anti-Stokes and Stokes type scattered light, as shown here. Okay, and it has a definite polarization which is perpendicular to the polarization of incident field. That's another sort of advantage, and that's linked with the fact that it's related to the Hall conductivity, not the ordinary conductivity that we usually work with. Okay.
Have you tested this? Sorry.
Experimentally, no. We do, you will see in the authors, Bhuvaneshwar is my PhD student, Mandar is an experimentalist from TIFR Bombay. So he did try, okay? But this we had suggested more than a year ago, and when it wasn't happening, we were a bit impatient to publish it, so it's published now. And Mandar is continuing his experiment still, and they have some signs of seeing first signal. But not conclusive.
Now many people must be trying differently.
Yes. Sorry?
Many people must be also
I
trying.
think in the world, yes. We received lots of inputs from people as soon as the work was published, yes.
What is the difficulty to test this one? Do you have a
Okay.
reason?
Yeah, the reasons are, see, terahertz window is a tough window of electromagnetic radiation. That's first sort of factor here. That you don't have easily available sources or detectors in terahertz frequency. That's one part. And second is it is a weak effect, meaning it's a non-linear effect. So it's not going to be spectacularly strong. But I do think, at least in the circuit mode, it should be easy to measure. And that's what Mandar is doing now. Mandar is expert in circuit-driven sort of measurements of devices. And
So what is the AC omega you have to give there?
This is the probe frequency,
Yeah.
omega AC or omega L. L can be light in the optical one, or omega can be omega AC if it's a circuit transport.
So, but if you're using a circuit, then how do you change the?
Then omega L will be replaced by omega AC. That's all. Really no change. It's
The experimental setup, if it is really a circuit ray setup,
yeah.
then you'll have to be using the omega AC as well.
Yes. So I'll show that.
Setting up the source itself will be a problem.
Yeah, I'll just show you what we did. No, so there we don't have a problem. That's what I wanted to tell you. Let me just get there. Yeah. So this is transport spectroscopy, and as I said, we are using frequency, vibrational frequency of 3.3 gigahertz. And the probe can be 0.1 to 1 gigahertz. That's easy to accomplish. That's why we think this is easier to do. Yeah.
But then it will separate out this here also.
Yes. So you will see if you. Sorry. I thought it had a video.
Yeah, I thought it was not separating.
Yeah, see the peak separate out. So that's why it should be very easy to verify in a circuit mode. I think there is some question online. I don't know who can. Okay, so sorry that some of it became a bit technical. Let me. Yeah. No question.
Only hand raise.
No, you just click on that view.
Okay, view. Here.
Hand raise.
Vinod Krishna. What are you trying to do? You can ask.
Directly you have to ask. You can ask directly.
Oh, in the meantime, can I ask?
Sure, yeah.
See, within the compass of the first principle theory, right? So what are the things that can be predicted? for example, I understand that you're worried only about quantum materials when it came to phases and things like that.
Sorry.
Hello?
Take that.
Yes, okay, sorry. Yes, please, I can hear you. Absolutely, yes. Yeah, so again, thank you for asking this question. Here, what we show is, unlike in free electron model, of course, there is no curvature, okay? But in an electronic system where the Berry curvature is non-zero in some part of the Brillouin zone, the trajectory of electrons near that band crossing where the Berry curvature is non-zero bends, which means there is a transverse velocity of electron drift along the transverse direction. So, and that happens without application of external magnetic field. Okay, so that's why it is a Hall effect, but it's an anomalous Hall effect because it doesn't require external magnetic field. No, sigma xy was zero if the curvature is zero. Sigma xy is direct. Yeah. Yeah, so again, it depends on whether we are talking about nonlinear or linear conductivity. In the nonlinear conductivity, we define Berry curvature dipole, which is like a, so that happens only when there is a single mirror plane symmetry in the system. Only then you can have a dipole which is perpendicular to that mirror plane. And then the Hall effect is perpendicular to that direction. Thanks. Yeah, Arun, you.
Yeah, see, I was just wondering what the compass of the first principle is before we got into.
Sure.
Can you use it to predictions about bulk properties like elasticity and other things which we normally use for statistical theory for?
Yeah.
And
Yes, so very much. I mean, that would be a separate talk. If you ask me, my major expertise is actually predicting bulk structural phase transitions using first principles theory and modeling. So it involves combination of first principles theory as I presented, combining it with statistical mechanics to predict temperature dependent elastic moduli or dielectric constants or many other measurable properties. But that requires one to go beyond first principles type of analysis. It's in principle possible.
the other thing I'm still not quite understanding the analogy. For example, we understand in the case of curvature and regular space-time. So there are two effects. There, I'm wondering whether this whole theory is still amenable with the usual GR way of doing things, right? We think of of writing a metric and looking at the differences in there. Not only you will get a time delay, but the phase that you're calculating will also change because of the path which you taken. So there's enough literature there.
I understand.
Which you can actually apply.
Sure.
Right. So you can formulate it using a Lagrange.
Absolutely. Yeah, it should be possible, I think.
So this very phasal differences can be actually possible.
Very phase differences are very readily measurable and also calculable. So what are more non-trivial are these curvature effects on all.
But the difference between this and GR is the space-time metric, the time.
Yes.
Which is not
That's right, yeah. Well, I mean, here we are looking at time evolution of electron.
Yeah, so here only because of the
Only
potential
the-
difference and then
Yes.
the path difference will come.
That's right.
But there, the time is not a part of the change.
Absolutely.
So thank you very much for this enlightening
Thank you.
lecture. It is very refreshing to listen to the lecture outside the domain of astronomy and astrophysics. I invite, yeah,
Any questions? You can ask them.
so I invite the audience to ask questions. Unfortunately, our handheld
Sorry.
microphones
Yeah.
are not working today. It's weekend, so please be loud. The people who are in the front rows, I think the microphones on the desk will capture it. But if you are sitting in the back side, please be louder. I will. If it is not the case, then I will repeat your question. So, yeah.
Yeah, so this is related to, I just want to make one comment related to what Arun asked. So I think that mathematics was worked out, probably the first one was Wilczek and Z, they wrote a paper on clarifying the fibobundle mathematics which goes into it.
Yeah.
That's just a side comment.
Yeah, that's the non-abelian Berry physics. Yes, yes, I'm familiar. Okay, so just to connect with that, my first PhD student's thesis was to show that one-year functions are eigenfunctions of non-abelian Berry matrices. Yeah.
So my question is related to the churn curvature that you were writing down.
Churn number.
So I felt that the fact that it is not an integer seems to be related to the fact that there is a non-trivial curvature of the underlying space coming up.
Mhm.
And it sort of, does it connect to something like a Gauss-Bonnet theorem?
Yeah, it is, yes, yes. So again, see, if it is an insulator where there is a clear separation between the manifold of occupied states and unoccupied states, Chern number is quantized, it's not a real number. It's real number continuous variable only when you work with metals where there is no gap separating. So you have a freedom of having flexible curve in the space along which you calculate it. So
there is a component which can, if you add it or subtract it, you can.
absolutely, yeah. So Chern number of holes plus Chern number of electrons is always quantized, for example.
I mean, I don't know if the analogy is correct or not, but that completion of a phase modulo 2 pi in that case. Right?
Yes.
That's the whole concept.
That's right.
And that is also related to the concept of Pancharatnam phase where the solid angle, when you proportional to the solid angle.
Mm-hmm.
Right?
Yeah.
There has to be.
Correct. And in physical sense, it's the polarization which is more defined only modulo quantum polarization then. Yes.
Yeah. Bani.
So my question is slightly different. So in solid state physics, we use X-ray crystallography to determine the structure of various things, and same technique is also used for many biological materials or biological systems like ribosomes or RNA and other things. But it becomes much more challenging there because it can damage the material and you still struggle to get edge structure. So will this transport spectroscopy, do you think it can help in determining the structure of biological materials?
Okay, thanks for raising this. It will measure vibrational frequency of a specific set of vibrational frequencies of a biomolecule, which is where Raman is also used presently. Lots of, there are Raman sort of markers of even diseases of certain biomolecular systems. So this will be useful within that sort of capacity. But in this case, you will need to deposit a biomolecule on an active substrate like graphene that I mentioned, and make sure they are not random. In biological molecular crystallography, you have to crystallize a biomolecule, for example, to do NMR or X-ray crystallography. Here, something like that may be needed as well, unless your measuring device is small and just one molecule is present. Then it won't need any sophistication of that sort.
Sure.
Yeah, so you talked about the circuit-based experiment. So I just want to understand what is the challenge in that? Is it you need the amplitudes have like as in the case of second harmonic generation, you need a really high intensity. So
Yeah, no, even the circuit signal is a nonlinear Hall signal,
yeah,
right, which is modulated by the vibrational frequency. So it is a weak signal. And in circuit, if you do circuit measurements, you always see noise
yeah.
also in many things, right? So, but our prediction says that this will be well beyond the noise. Yeah, certain peaks will be should be visible, and actually we think they are already probably seen, but people may not have realized them.
Okay, so it's just the detection.
I think so. It does need
Not the input.
yeah. For example, when I spoke to Professor Chandani in IISc about this work, and she does Hall measurements also using similar materials, and they never look at the frequency range that we are talking about, right, for the Hall signal, because their focus has been very different. So my response to her also was, I'm sure this signal is there, we need to look for it. Yeah.
Yeah, so I am just trying to understand in density functional theory you described. So each atom and its electronic configuration is not, it can give energy in the ground state, but using the density function for the electrons, you can get the same energy, right? If I am getting right. DFT theory suggests that you don't need to go orbital contribution of each electron to know the total ground state energy. But if we take a molecule as a whole, and then another molecule. So interaction between those molecules can be via different forces, like it can be ionic, covalent, van der Waals forces. So how means DFT can even calculate those forces in terms of just
So, no, so I first of all want to add to what your first point is. DFT is not addition of orbital energies or contribution of each electron to the energy. That's not what I gave a message. It is in principle an exact theory for many electron ground state, quantum mechanical ground state. It's in principle exact. So you have one molecule or a collection of molecules, doesn't matter. It should give you the many electron ground state energy of electrons. And if you add internuclear Coulomb interaction to it, you have the total energy available. Now, of course, this is in principle. In practice, it's not so exact, because I told you we use approximations for the functional that we have. And in fact, van der Waals interaction was not captured by most of the commonly used density functionals for a long time. So only recently there has been a lot of progress in capturing these weak interactions accurately enough within density functional theory. So DFT captures, of course, ionic and covalent interactions, but they also capture this other type of multi-bond interaction. In chemistry, you may have 3 electrons, 5 pole center bond, for example. Those are also captured very accurately.
So the chemical reaction can be predicted if we have the exact DFT value, right?
Yeah, well, again, so if you start exciting electrons, see, I said electrons are in many electron quantum ground state. If your observation or measurement involves exciting electrons, then you need to do a lot more work. The framework that I introduced to you is essentially within the adiabatic approximation, where electrons are assumed to remain in the quantum ground state. So elastic properties that Arun asked are directly just second derivatives of the total energy with respect to lattice constant, or dielectric constant is second derivative with respect to electric field, and so on. So they are directly accessible.
The question, in fact.
In that Hall spectroscopy changes where you said that AC frequency changes and that gives the different peak. So what are the physical significance of that when it is changing the AC frequency? And in general, what kind of other frequencies are using and what's the difference in that?
Okay.
And why using AC frequency?
AC because, okay, because we are here relying on nonlinear Hall effect. So for example, this is optical. You are asking transport, right? Okay, yeah. This is a device where you have AC field is applied along the drain to source, right? And since it's nonlinear, the frequencies which are generated here are either 2 omega or 0 in the absence of any vibrations. And what we show is if you have vibrations in the system, it will have additional peaks in the spectrum, and those are the peaks I'm showing you. Now, you don't have to change AC frequency to study this. Like in Raman spectroscopy, you often use one specific visible light frequency to see the scattering. In this case also, you could do only one specific AC frequency, but if you want to really systematically capture, you will see if I change AC frequency in this case, I'm going from 1 gigahertz to 3 gigahertz, 4, 5, the peaks separate away from the vibrational frequency. So this gives you more confidence in the fact that you are measuring the peak that you are thinking about. For example, there was a question about, do you see these things in circuit measurements? And I said, probably people haven't looked for them. And one way to make sure that this is the peak we are predicting, you can vary AC frequency and see systematically whether that variation is there. If it is, then certainly this is the peak, proposed peak.
So I don't see any hand raised, so are there any, if there's a question from online, please, you can unmute and ask. If that is not the case, then then I invite the Professor Annapurni to honor our speaker by handing over the memento and the small token of appreciation for your time.
This is a picture of the night sky taken from one of the observatories. So.
Thank you, it's lovely.